Velocity time graphs really tell the story of an object's velocity over a given time. In this simple little journey, we can see that the car accelerated or increased its velocity over the first 2 seconds. And then after 2 seconds to 5 seconds, it was going at a constant velocity until it finally came to rest after 1 second, or it de-accelerated. One of the most important things we can get from a velocity time graph is the acceleration of the object at different parts of its journey. And we know we can work out the acceleration of any object because acceleration is equal to the final velocity, take away the starting velocity, and divide that by the time taken for that to happen. In other words, the acceleration of a velocity time graph is really the gradient of that part of the graph. And we can just have a quick look at this graph and decide what's happening. For example, in the first part of the journey, we see we're going to have a positive gradient, which means we're going to be accelerating. The second part of the journey, we can see we're going to have no gradient, it's flat, so we're going to have no acceleration. And the final part of the journey, where it goes from 8 meters per second down to 0, it must be slowing down, or as we say in physics, it must have negative acceleration, or another way of putting that, it must have deceleration. So from a velocity time graph, we can look at it and we can get a feel for the different accelerations taking place. We can actually calculate them using our formula. So let's split up the journey in terms of parts of the journey. We'll call this part of the journey A to B, and then from B to C, and C to D. And to work out acceleration is really quite simple. So from A to B, the acceleration would be equal to the final velocity, which we know is going to be 8. Take away the starting velocity, which we know is going to be 0, and put a bracket around that, and divide it by the time it took to do that. It took 2 seconds to do that. So when you have acceleration is going to be 8 divided by 2 is going to equal to 4, and the units are meters per second per second. Let's look at the graph and see how that matches up. 4 meters per second means every second the velocity is going to increase by 4 meters per second. Gotcha. Another second, it's increased by another 4 meters per second to give us 8 meters per second. Now, the journey B to C, we can see that the gradient is flat. There is no change in the velocity, and if there's no change in the velocity, we can say that the acceleration is going to be equal to 0. What about the final part of the journey from C to D? Well, we do the same thing again. Our final velocity this time is 0, it's stopped. So we can put down acceleration is equal to final velocity 0, take away the starting velocity, and the starting velocity up here was 8 meters per second. So 0, take away 8, be careful, you're going to get a minus sign, and you divide that by the time it took to do that, and it took 1 second to do that. So we divide it by 1 second. So we get an answer of minus 8 meters per second per second. Well, let's match this up on the graph. That means that every second you're going to lose 8 meters per second of your velocity. So we start at 8, and 1 second later we're down to 0. We've lost 8 meters per second. So the first important part of a velocity time graph as basic form is that we can work out the accelerations at different parts of the journey by using our acceleration formula.
Physics is wonderful! Physics is cool!